Hi there and welcome back here to section 2, if you will. Let's put this together and develop the whole story relevant to wind forecasting. And again, what we're trying to do is to make our own wind speed and wind direction forecast based on a simple weather map. So let's have a look. Again, upper atmosphere versus lower atmosphere. Upper atmosphere, hey, you got two forces, pressure gradient force, Coriolis force. Lower atmosphere, close to the ground surface, you still have the pressure gradient force, you still have the Coriolis force, but you also have the friction force. And now, basically, what the wind has to do is to obey, if you will, whatever forces are acting on it. Right? In the upper atmosphere, well, you got two forces, and the way the wind can handle that and can say, well, all right, I'll do what both of you want me to do, and the way I can do this is by blowing parallel to the isobars. And the wind that blows parallel to the isobars, we call it geostrophic wind. Right? In the lower atmosphere, well, you just have to add one more force to it, which is the friction force. And then what the wind has to do is to compromise, if you will, between three forces. And the wind can do that simply by blowing across the isobars at an angle. That's basically the laws of physics reduced to two sentences, if you will. Right? So this is schematically illustrated here as a simple pressure gradient from high pressure to low pressure. Near the Earth's surface, we have the pink wind direction at an angle across the isobars. And in the upper atmosphere, we have the purple wind direction, geostrophically parallel to the isobars. Now, we can draw this now not as a gradient, but as a pressure hill, if you will, and as a pressure hole, if you will. Same here, pressure hole, pressure hill. And the wind has to blow down the hill, gets deflected to the right, and crosses the isobars at an angle. And here, the wind spirals in, if you will, converges into the pressure hole, flows down the hole, if you will, down into the hole, spiraling in, crossing the isobars at an angle. That's the lower atmosphere. In the upper atmosphere, once you're high up, friction doesn't matter, and the winds blow parallel to the isobars, around the high pressure area, parallel to the isobars, around the low pressure area. That's the whole story. And then here's your animation. We looked at this before. This would be the situation, hypothetically speaking, if the Earth were not rotating. Here we have a situation where all we have is a pressure gradient, and the wind blows straight down the pressure gradient from high pressure to low pressure. Right? There's only one force, because there's no Coriolis force. There is no deflection. That's not how it works, unfortunately, because the Earth is rotating, and this is what happens in the upper atmosphere. Right now you have the pressure gradient force shown in red, you have the Coriolis force deflecting the wind in black. They balance each other, therefore wind direction is parallel to the isobars. So that's good. At the surface, it gets a little bit more complicated because now you have to account for friction. Let's look at the surface wind patterns. First of all, overall, you notice that the wind speeds are slower. The green arrow isn't moving as fast. Well, that's because of friction. So you have three forces going on right now. Pressure gradient force in red, Coriolis force in black, friction force in blue. And when you add those up, according to the laws of physics, the only thing that is possible is the wind blowing diagonally across the isobars, crossing the isobars at an angle. Let's look at the same thing with a high pressure cell. Imagine the wind flowing down the hill, if you will, from this hill down the pressure gradient. Well, let's look at the surface. Start right there. Well, there we go. The wind is blowing outwards, it's flowing down the pressure hill. As it does so, it gets deflected to the right by the Coriolis force. and it gets slowed down by the friction force, and therefore it has to blow across the isobars at an angle. Let's look at the same thing in the upper atmosphere. First of all, notice how much faster the arrows are moving. Well, that makes sense because we are in the upper atmosphere. There's no friction. Wind is blowing parallel to the isobars because there's only two forces. They balance each other out. Therefore, we have a geostrophic wind parallel to the isobars. And then if we would stop the Earth from rotating, Coriolis force would cease to exist, and the wind would blow straight down the pressure gradient, going across the isobars at a 90-degree angle. All right. Let's make wind predictions. Let's take what we've just sort of learned in terms of facts and put this all together. And really, when you deal with wind, it's really one of those things. You have to ask yourself a question. Are you predicting wind in the lower atmosphere, or are you predicting wind in the upper atmosphere? Because depending on where you are, if you're close to the ground or high up, different rules apply. Lower atmosphere. Wind direction is controlled by the pressure gradient force, the deflecting Coriolis force, the slowing friction force. Wind speed is a function of the pressure gradient and the amount of friction. Winds blow across the isobars at an angle. They never blow parallel to the isobars. They never blow perpendicular to the isobars. Here's the upper atmosphere. In the upper atmosphere, wind direction is controlled by the pressure gradient force and the Coriolis force. There is no friction force. Wind speed, therefore, is only a function of the pressure gradient. Winds have to blow parallel to the isobars. They can never ever cross the isobars. So this, if you will here, is your little cheat sheet index card for wind speed and wind direction. Now, let's take this apart for prediction in the upper atmosphere first. All right. Upper atmosphere, right? If you will, the air gets sort of kicked or set in motion by the pressure gradient force. So now there's a pressure gradient. Your air parcel starts to move from high pressure to low pressure. As it starts to move, it gets deflected. And that pull to the right in the northern hemisphere eventually leads the wind to blow parallel to the isobars, and we call that geostrophic wind. And just to have one last sort of illustration how that works, if you have a pressure hill or a pressure hole, the winds blow in towards the low pressure, get deflected to the right, and then they end up going parallel to the isobars counterclockwise once the pressure gradient force is balanced by the Coriolis force. There's actually a real point to all of this, and that's called the jet stream. Right? The jet stream is this wind system we have in the upper atmosphere that blows parallel to the isobars all around the world. And why is that? You can think about it this way, simplistically speaking. There tends to be always high pressure over Mexico. There tends to be always low pressure over Canada. So therefore, there's always sort of a pressure gradient that tries to make the wind blow from Mexico towards Canada. And as the wind starts to blow, it gets deflected to the right. And we're in the upper atmosphere, there's no friction. So there's always a wind blowing more or less from west to east over the country, around the world, parallel to the isobars. And we call that the jet stream. So here's an example. Here's a weather map. Now it looks a little bit confusing, lots of lines and numbers and letters, right? But as with any complicated thing, you just pick it apart piece by piece. And the first thing you want to look for is where are the high pressure areas, where are the lows, and then you look at the isobars. So first, let's find the highs and the lows on this map. Well, there we go. I circled them for you, right? High pressure area here, high pressure area here, right? This is Baja California here, so this is Mexico. High pressure area here, this is Cuba, this is Florida. And then there's a low pressure area here, this is over Alaska. Another low pressure area here, this is Hudson Bay. And then sort of a low pressure area out here, Labrador. So you have a basic pressure gradient from, if you will, Mexico across the United States to Canada. And then those lines here, those are the isobars. And remember, you're in the upper atmosphere. So wind cannot go across the isobars. So you can just draw in the wind direction. And that's the wind direction on this particular day. Right? Wind was blowing from west to east. Had a big dip here over California, but nonetheless. And then across the country and out into the Atlantic Ocean. Why? Because it can't blow across the isobars. You're in the upper atmosphere. The wind has to blow parallel to the isobars. So that's the wind direction. Why is that important? Well, the jet stream is important for many reasons. Right? It's sort of the boundary, if you will, between sort of the warmer air in the southern part of the United States and the chillier air or colder air over Canada. And that boundary, that demarcation, is basically the jet stream. Basically, this girdling wind system that blows right around the Earth in the mid-latitudes from west to east. That's, for example, why it takes longer with an airplane to fly from Boston to San Francisco than it takes from San Francisco to fly to Boston. Actually, about an hour. Why is that? Because if you fly from San Francisco to Boston, the jet stream is pushing you. You got a tailwind. If you're flying from Boston to San Francisco, you're flying into the jet stream. You're flying into a headwind. That's also the reason why our weather always comes from the west, because the storms and rain and clouds and tornadoes and whatever the case might be are blown across the country by the jet stream. So if you want to think about weather in New England is blown towards us by the jet stream. Lower atmosphere. Right? Might be more interesting because that's where we live. Again, friction. Below about 5,000 feet, if you're closer than that to the Earth's surface, the wind simply experiences friction. That reduces the wind speed. Friction reduces only the wind speed, but of course it has no impact on the pressure gradient force. And if you have less wind speed, laws of physics dictate that you have less Coriolis force deflection. That means your pressure gradient force will be dominant. That means your wind will only get partially deflected, and the winds have to blow diagonally across the isobars. That's why anytime you see wind speed or wind directions in the lower atmosphere, they always cross the isobars at an angle, such as that pink line. All of these arrows here, they always go across the isobar sort of at a 30 or 45 degree angle. Well, that's because that's what physics dictates. Right? In the lower atmosphere, winds have to cross the isobars at an angle. So you can take a weather map such as the one below, simplify it. In this particular case, we have one big high pressure area, we have one big low pressure area. Right? And you can think about a high pressure area as a big blob of cold, heavy, sinking air that creates a big pile, a big mountain at the Earth's surface. And then the winds flow out or flow down that pile, diverge, if you will, out of that pile, crossing the isobars at an angle. You can think of a low pressure area, if you will, as warm air rising, effectively leaving a gap, leaving a hole of air behind. Right? There's just less air there. Therefore, winds blow into that gap, if you will. They converge into the low pressure area, crossing the isobars at an angle. So all of these arrows are more or less crossing the isobars at an angle, because that's what they have to, according to the laws of physics. In the lower atmosphere, winds cannot blow parallel to the isobars. And of course, because the Earth is rotating, winds can never blow down, straight down the pressure gradient. Here's a real weather map. Again, areas of high pressure giving you piles of air, if you will. Areas of low pressure giving you gaps of air, if you will. And now you got a pressure gradient. Awesome. That sets the air in motion. As the air is blowing, the air gets deflected to the right with the northern hemisphere. We have friction, so therefore winds have to cross the isobars at an angle. So what's the wind direction on this particular day, November 12th, 2010? Well, oops. There we are. Sorry about that. Right? Well, winds have to blow down the pressure gradient, crossing the isobars at an angle. Winds have to blow into the low pressure area, crossing the isobars at an angle. Once more, here's your cheat sheet. This is really all you need to know about wind forecasting. That's what the weather forecasters on TV use. Are you in the lower atmosphere? Are you in the upper atmosphere? That's the first question, because you have to know whether or not you're dealing with friction or you're not dealing with friction. And then depending on what the situation is, in the lower atmosphere with friction, winds blow across the isobars at an angle, or in the upper atmosphere, because there is no friction, winds can blow geostrophically parallel to the isobars. As a comparison, right? We have the surface of the Earth, and we have right above us the upper atmosphere. Imagine you stand right out here, and then you look up. And as you go up, 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 at some point, let's say you're 5,000, 6,000 feet above the Earth's surface, this would be the wind direction. You got high pressure, you got low pressure, you got a pressure gradient, no friction, wind has to blow parallel to the isobars. Near the Earth's surface, where you're standing, wind direction is a little bit different, right? Because you have friction force and the winds blow diagonally across the isobars. So that's actually kind of interesting. So if you're standing around, whatever the wind direction is near the Earth's surface, if you were to go up in your hot air balloon, up, 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 at some point, once you reach about 5,000 feet above ground, the wind direction would shift from whatever it is to parallel to the isobars. That's called wind shear, actually. The fact that the wind direction changes depending on where you are in the atmosphere. Similar diagram, now we're looking at pressure hills or pressure gaps, pressure gaps, pressure hills. Upper atmosphere, winds have to blow parallel to the isobars. Near the Earth's surface, winds are spiraling out of the high pressure area, crossing the isobars at an angle. Here's our pressure hole or gap. Winds are spiraling in, blowing around the hole, if you will, parallel to the isobars. And in the northern hemisphere, near the Earth's surface, winds are blowing into the low pressure area, get deflected to the right, and they're converging, crossing the isobars at an angle. And then we can finally look at our animation for the last time. Surface, high pressure cell. Surface, high pressure cell. There we go. That's your pile of air. That's your sinking cold air, giving you a pile of air molecules lying around on the Earth's surface. And the air just flows down this hill, gets deflected to the right, gets slowed down by friction, and there you have the winds crossing the isobars at an angle. In the upper atmosphere, everything is faster, but there is no friction, therefore the Coriolis force is strong enough to match the pressure gradient force, and the wind has to blow parallel to the isobars. And now if we can just make the Earth rotation stop, there is no Coriolis force, and all the wind can do is go down the pressure gradient perpendicular to the isobars. That is the wind story. So now you can take any old weather map and you can do your own wind forecasting, both in terms of the direction of the wind, but also the speed of the wind. Direction is always generally from high pressure to low pressure, and your wind always crosses the isobars diagonally at an angle. Speed, if you have a steep pressure gradient, wind is going to be fast. If you have a flat gradient, wind is going to be slow. So all you got to do is look at your weather map, find your high pressure areas, and find your low pressure areas, and then look at the white lines, look at your isobars. Pretty tightly spaced here, it's going to be pretty fast, pretty windy in here. Same out here, by the way, over the Atlantic Ocean. In contrast, here you have a very wide spacing. Gonna be pretty slow here over Indiana. Right. So now we just need directions. You can draw these in mentally if you want to hit the pause button. And there you go. High pressure hill, pile of high pressure air here, flowing down the hill, crossing the isobars at an angle. And here's our low pressure area. Our wind is blowing into the low pressure area and gets deflected to the right. As it does so, the air is spiraling into that low pressure area. So again, it's all about where's the high pressure, where's the low pressure. Winds have to go at an angle across the isobars. Steep gradient means fast wind. Gentle gradient means slow wind. That's all you need for wind forecasting. And that's how you make a map like this. So you can go to any old website, whether that's weather.com, AccuWeather, and you can find these wind maps where they show you the direction of the wind and the speed of the wind. And all they did was use exactly the rules that we've just established. All right? So in the last section, we're going to go a little bit big and expand this out a little bit and look ahead on why all this is important in terms of atmospheric circulation.